So, Chapter 8 is about vectors, and so we will be looking at several different things about vectors. So today we're going to start sort of with an overview of what they are, and then we're going to look at the vectors that are within context. Then we also have to look at some algebraic vectors that we'll look at on, well, actually we probably won't get to those till maybe Tuesday or Wednesday because we'll do a few more in context vectors on Monday. So a vector is something that you're going to see a lot. If you take a physics class in college, you're going to see a lot of vectors. It's basically the majority of what I remember physics being about whenever I took it. It's been quite a while since I took physics, and I haven't used it much since. But physics involves a lot of vectors. And I like vectors because although the problems I'm going to give you are sort of, high school problems that have been simplified down, you could see where this stuff would sort of apply. Whenever my husband was in engineering school, they would do a lot of different, like he had one class on that was called statics. And statics was a class on building things that sit still. So like whenever you see a sign over the highway, right, you got a big pole and then you got one of those big signs that holds up the, turn here, exit coming up signs. There has to be a lot that goes into figuring out that sign. Now, once you get one engineered, you can probably use it in different places. But for those signs, there's a lot of weight in that sign and the supports going across the highway there, and you definitely don't want one of those signs to come crashing down on the cars passing by. So you have to figure all the different forces that you have. You have to consider things like the forces of the wind and things like that may blow against that sign. And it's got to be strong enough to withhold all of those forces so it doesn't crash down in the middle of the highway. So you can take a lot of this stuff to really far lengths. One of my husband's roommate in college, he works for a company that designs cell phone towers. So that's what he does all day. And some of these cell phone towers are like super crazy tall. There are cell phone towers that are taller than like skyscrapers, like taller than the tallest buildings. So I don't know that he necessarily designs those, but there are, there's a lot that goes into those because you have this if you think of like taking your pencil and trying to balance it on the desk, because that looks about like a cell phone tower, right? It's just a tall, skinny pole. It kind of looks like. It doesn't balance on the desk very well, right? So if you've got something that tall and skinny, you've got to have the right supports and know the different forces and stuff that are going to be on that and how, far your supports need to go down into the earth, what kind of all those wires coming off that support the tower where they need to be to make sure that your giant cell phone tower doesn't go crashing down on top of something. So, and then everybody loses their cell service and they're terribly upset. Plus somebody might get crushed by the tower. There's a lot of stuff like that this stuff can be taken much, much, much further. We're just going to get sort of an overview of it, but I think it's kind of interesting. So, a vector is a quantity that has both magnitude and direction. There is one vector you have probably already heard about a lot, but you might not know it as a vector. Have you guys heard the word velocity before? And when I say velocity, what do you think about? Speed, right? But velocity and speed have a difference. Does anybody know what that difference is? It's not your time, because both of them, like speed would be in miles per hour, velocity would also be miles per hour or feet per second. It is direction. Velocity has direction. Speed has no direction. So whenever I ask you how fast you go whenever you drive from here to Winston, or your average speed from here to Winston, you're going to tell me, 65 miles per hour, or whatever it may be. You are not going to tell me negative 65 miles per hour, because you're going away from our current location. But with velocity, you have direction and you have what we call magnitude, which the magnitude part is your speed. So velocity always has direction, although often we might use it in conversation like it doesn't. We might use it interchangeably with speed, but technically it's not. So a vector can be represented geometrically by a directed line segment. And this is where this fits into our current study. So far we've been doing a lot of stuff with triangles. We've been doing law of sines and cosines and all of that stuff. So what we're going to do with these vectors, we're going to represent them geometrically by a directed line segment. So the length of that line segment is the magnitude, or if it were velocity, it would be the speed. And if a vector is in standard position, the direction of the vector is the angle between the positive x-axis and the vector. And I don't know why there's a tiny r right there. But so, for example, if I had a vector, it is drawn as a directed line segment, which really whenever you were, well, you didn't take geometry, so you may or may not have ever really used array. You guys remember learning about array? When you learn about angles, it's two rays together. So it looks like a ray is what it looks like. You've got an end point, you've got an arrow on the end. It's technically not a ray because this arrow here just tells you direction. It doesn't really mean that it goes on forever in this case, but it looks like a ray. So like if I have this vector right here, the length of that vector, how long it is, so let's say that this is 6 centimeters, that's my magnitude. Would be the length of your vector. Your direction of your vector, if it's in standard position, it's the angle between the positive x-axis and the vector. So that would mean you start right here at 0 and you go around to this point. So, you know, I don't know, that might be like 150 degrees. So we would say that that vector has a magnitude of 6 and a direction of 150 degrees. So we're going to start off with just some like very general vectors. We're going to first sketch a vector. And since we're only going to do one, and they definitely cannot make you sketch a vector on the final exam whenever it's multiple choice, I'm not going to take the time to pass out protractors and rulers, but you guys can kind of watch to get the idea. So if we're sketching a vector that has a magnitude of 3.6 and whose direction is 30 degrees, I would need to have a protractor and a ruler. So let me find mine here. So if I line up my protractor here, 30 degrees is the angle right here. And then I need a magnitude of 3.6. So you could use inches or feet. It really doesn't. Inches or centimeters. I'm going to use centimeters here because it was easier to do 3.6 with that. So if I measure the length here, it's 3.6. It's actually very close to that dot that I put there, which is just coincidence. Let me actually do this. Better. Start right here. 3.6 is right here. So if I had to draw this vector to scale, this is what it would look like. The length of this here would be 3.6, and this angle right here would be 30 degrees. When we get to the more difficult problems, which we will do on Monday, we're going to actually use a ruler and a protractor and draw them to scale, because if you don't draw them to scale, sometimes it's very hard to tell what the actual answer is. Today we're going to be doing the ones that are a little more simple, so we won't be doing that too much. So let's go here. So when you're adding vectors, there are two ways to add vectors, and the two ways to add vectors are the triangle method and the parallelogram method. I used to always use triangle method. I like it personally better, but I have decided last semester I taught parallelogram method, and I think that I'm weird for using triangle method, and that most people probably like parallelogram method better, so I think that's what we're going to go with here, although you could use either, so I'm going to show you both. So here we have two vectors. They're not specific vectors, they're just pictures of vectors. Because I can, I'm going to copy and paste these two vectors. You can't actually do that, but you can, hold on, copy this one, copy, paste. So if I'm adding these two vectors, the first way that you could find the resultant vector is you could take this vector and then take the second vector and put the dot of the second vector at the end of the arrow of the first vector. Alright, so you take vector number 1, you draw it, you take vector number 2, and you add it in here. So you might want to sort of sketch that. So this one here, this is number 1, this is number 2. So right here you can see that's the same vector as number 1, that's the same vector as number 2. And the resultant vector is the vector that goes from your starting point, so the starting point of that first vector, to the arrow of the second vector. So it would look like this. This is your resultant. Okay, the other method that you can use is called the parallelogram method. So I've got the same two vectors here. Let me change their colors. Let me make this one blue and this one, hold on, green. So if I copy these vectors, Alright, so the other way that you can do this is you could take both of the vectors and put their starting points together, like this. And then, when you do that, you're going to take these two pieces and you're going to make a parallelogram. If you make a parallelogram, I can copy and paste. You're just going to have to kind of, yes. So it makes this side, let me make this a dotted line. Okay. And this side, would look like this. So you make a parallelogram out of that. Alright, and then the resultant, if you use parallelogram method, is from the common starting point to the common arrows at the end. So this would be your resultant. Now, if you look back up at the one we just did, we started with the same vectors in both cases. Our resultant, it looks the same in both cases, right? If you look at this parallelogram, it really is just like this half of it is our triangle method. So either way is a way that you can look at these for this problem. I am probably going to use parallelogram method more often for these problems because it seemed to go a little better last semester in parallelogram, especially once you get to the more difficult problems. Okay, now, I know that when I first learned about these, this seems like sort of crazy nonsense at the beginning. You're adding all these arrows together. So we still got to do a little more crazy nonsense. We're going to do these like weird vectors that are just vectors for vector's sake. But then in the next problem, we'll look at an application, and I hope it'll start to make a little more sense of where you could apply this. So a vector symbol looks like sort of it looks like an arrow that has been cut in half. I can't type it on my smartboard program, so I have to draw in these little vector symbols. But if you see a lowercase letter, typically it's going to be bold, but maybe not always, and it has this little half arrow over it. That means vector A. So if vector A has a magnitude of 3 and a direction of 90 degrees, and vector B has a magnitude of 4 and a direction of 180 degrees, and C equals A plus B, find the direction and magnitude of C. Okay. So for this, I always start with sort of like an XY axis here. And you'll notice our directions here are 90 and 180, which is going to be, yeah, they're on the axes, right? So that makes these problems a little bit easier to deal with. So I typically, in this case, on these easier problems, I usually don't draw them to scale. I try to draw them kind of to scale. I make the length of side 3 a little bit shorter than the length of side 4, but I don't get out the ruler and make it perfect. When we get to the difficult problems, we're actually going to draw these to scale. So, so we've got a magnitude of 3 here, so I'm going to use blue for my first one. So 90 degrees would almost be like north if you're thinking this way. So we've got a magnitude of 3. And then we have a magnitude of 4 that goes in the 180 degree direction. So that would be here. And so to use parallelogram method, here's, we know this side has a length of 3. We know this side has a length of 4. To use parallelogram method, let me show you what most people usually do wrong. They will do this. They'll just make a triangle right there. Okay, that is not correct. Because parallelogram method says we've got to make us a parallelogram here, which actually is a rectangle. Right, so we make us a rectangle here. It's not a perfect rectangle, but good enough. And then our resultant vector goes from the common starting point to the common, I really should make these arrows, to that common, this common arrows right here. So this is my resultant. So I need to know the magnitude of that red vector. I also need to know the angle of that red vector. So the magnitude, I think, is the easier part. So if this side right here is 4, this side right here is also 4. Or if this side is 3, and this side right here is also 3. And in this particular case, we're dealing with a right triangle because 90 degrees and 180 degrees are perpendicular to each other. So since that's a right triangle, and I know 2 sides of the triangle, what can I use? Pythagorean theorem. So I can say 3 squared plus 4 squared equals C squared. And so I've got 9 plus 16 equals C squared. You probably already know the answer to this one. We're going to square root both sides. 5 is C. So the magnitude which we represent geometrically by the length, our magnitude is 5. Now for our direction, we always want to start at the x-axis, positive x-axis here, and we want the angle that will go all the way around to the vector that we're looking at, always counterclockwise. So if we want that angle right there, we really can't find that angle right off. But I know this part right here would be 90 degrees, right? So if I could find, I'm going to call this right here theta, if I could find that angle right there inside of that triangle, then I could just add 90 to it, and that would be my direction. So you could use law of sines here. But I want us to go back and review a little bit of regular trig, because I may have let you guys rely on law of sines a little too much in the last section. Because, obviously most of the problems you had to use law of sines, but when you get down to the end of those problems, sometimes you could just use regular trig if you have right angles, but a lot of you did not. So let's just review real quick. If I have a triangle, say I've got a triangle that looks like this, and this is my right angle, and this is the angle that I'm looking at. So if I've got sine of theta, sine equals what? There's opposite, adjacent, hypotenuse. It is opposite over hypotenuse, right? What about cosine of theta? Adjacent over hypotenuse, and tangent is opposite over adjacent. So you might have learned several different things. There was SOHCAHTOA maybe, or some old hippie caught another hippie tripping on acid. There's that one. My husband, who had the same geometry teacher as me, yeah, I don't know where he really picked this up. He would say Oscar has a hairy old arm, or whatever other A word that you would like to replace that with there. So I don't really know where he picked that up, because our geometry teacher did not teach that. But several things you can remember these with. So if we look at this triangle right here, and we want to find this angle, 4, is that my opposite, adjacent, or hypotenuse? It is opposite. It is across from the triangle. It does not touch that angle at all. So it is opposite. And 3, is that opposite, adjacent, or hypotenuse? It is adjacent. So if I'm dealing with opposite and adjacent, then I need to use tangent. So I would say tangent of theta equals opposite, which is 4, over adjacent, which is 3. And how do you undo tangent so you can get that angle by itself? Inverse tangent. So you'll do inverse tangent of 4 over 3. And if we do inverse tangent of 4 over 3, we're going to get theta is 53.130 degrees. But that's not my answer. That's not my direction, because that's just this part right here. I want to start from the x-axis, positive x-axis, and go to that. So I'll have to add 90 to it. And when I do that, I'll get 143.130 degrees, and that is my direction. So we have magnitude is 5, direction is 143.130. Okay, questions? Okay, so all of this still, it's kind of like not really adding up what you would do with this. So example 2 is going to start to give us a picture of what this looks like whenever you start to apply it to a situation. I said earlier, vectors are used a lot for forces. One in particular that you can consider are wind forces, forces that are caused by the wind. So, and as I mentioned with the signs also, you got to, wind can really do a lot of damage whenever you've got things that are being, like especially large flat surfaces being pushed by the wind. So a wind blowing can be represented by a vector. The vector has an eastward component and a northward component. If the eastward component has a magnitude of 20 miles per hour and the northward component has a magnitude of 8 miles per hour, in what direction is the wind blowing? So there's several ways you can think about this. You can, although it's a wind that's blowing, we know it's going to be northwest in some direction, right? But although we can think of a wind that's blowing north and west, and we want to know what each piece, we want to know when you put those two pieces together what it is. You can also sort of think of, although it's not quite what's happening here, is you can think of like you have a fan that is blowing eastward at 20 miles per hour. You have another fan that blows 8 miles per hour northward. You want to see whenever those two cross what direction the wind takes off in, right? I think that's kind of easier to think of if we were like creating this situation, right? So with all of these, I usually start with X and Y axis. I know that I have a northward component and an eastward component, so I really don't need a lot of room. Oh, let's see. I really don't need a lot of room for the south and the west side, so I'm going to leave myself more room here. And I know that one component of the wind is eastward with a magnitude of 20. So if I draw in a vector starting right here, and it's going to the east at 20 miles per hour, and I also draw in a vector going to the north, it's only 8 miles per hour, so I'm going to draw it shorter here. And I'm going to label those. This is 20 miles per hour. And this is 8 miles per hour. And remember that we must make a parallelogram here. Because if we just do this, which is the major mistake everybody makes, if we just start connecting here and making this a right triangle, you'll get the right magnitude. You'll get the right wind speed, but you won't get the right direction. Because if you have wind blowing north and east, it's not going to be going in this direction, right? It's going to be going this way somehow. So we got to make us a parallelogram. So if we kind of draw in this side, this side here, this side would also be 20. This side would also be 8. And our resultant vector is going to start where those two started, and it will end at the across the parallelogram there. Okay, so this should sort of make sense. It should be going like kind of further to the east than it is to the north because your eastward component is stronger. It did not ask us to find the wind speed at all. If it did, we would do Pythagorean theorem, right? We'd do 8 squared plus 20 squared equals c squared, and we would find that wind speed. But it doesn't ask us about that. It only asks us about the direction that the wind is blowing. So we need to find this angle right here. And so we know 8 and we know 20. Destiny, 8, is that opposite, adjacent, or hypotenuse? It is opposite. And Liliana, 20, opposite, adjacent, or hypotenuse? Adjacent. So, Matt, if we have opposite and adjacent, what should we use? Sine, cosine, or tangent? Tangent, right? So we will say tangent of theta equals 8 over 20. And Emily, what do we do to get rid of tangent? How do we solve that? Inverse. So we do inverse tangent of 8 over 20. And so when we do that, inverse tangent of 8 over 20 is going to give us theta is 21.801 degrees. Now here's the thing. If you get a question like this, and it has north, south, east, west in the problem, they're probably not going to give an answer where it's just that angle. Like in the last problem, if they just give you angles, 90 degrees and 180 degrees, the answer is just going to be the angle from the positive x-axis over to this point. So like here, 143.130 is your answer. But if it has north, south, east, and west in the problem, it's going to have north, south, east, and west in the answer. So if we're looking at this problem, and I think this is a little bit confusing, all right, if I look at that angle, which side does it actually touch? North, south, east, or west? Okay, which of these directions, north, south, west, or east, which one of them actually shares a side with the angle? East, right? So it actually shares a side with the angle. So that means in this particular case, east is going to be our main direction. So we would say in this particular case, 21.801 degrees north of east. Whichever is your main direction, whichever one the angle actually touches, that goes last. So north of east. So east is your main direction. You're going 21.801 degrees to the north of that. Here's the other trick on these problems. Sometimes these are multiple choice. Sometimes that answer choice is not there. Okay? If this is 21.801, now I just chose to find this angle. I could have found this angle right here. Right? I could have used that other triangle. So if I had done that, if I do 90 minus the answer that I just found, this angle right here is 68.199 degrees. Alright, so 21.801 degrees north of east, that is an answer. But 68.199 degrees is also an answer, except it is east of north. Because if you trace, let me use a different color, if you trace that angle, the 68.199, then the side that it actually touches is north. So it's 68.199 degrees to the east of north. Okay? Whenever we take a quiz on this stuff, it is going to be open-ended. So you will write your answer down. So you can give me either one of those answers, and the answer is correct. Just make sure you got your north and east in the correct order for whichever answer you put. You don't have to try to give me both. Just give me one of the two answers, and it's correct. Whenever you get to your tests, I believe there are going to be some multiple choice questions on these. And so whenever you see these on a test, if you get 21.801 but realize your answer is not there, check and see if the complementary angle, or complementary angle to that would work. Okay. All right, let's do another one. Okay. These problems I really like because I think they're kind of easy to visualize. Now, in real life, it's not quite this easy because the wind does not usually blow perfectly out of the north. The plane is usually not flying perfectly east. Usually it's at different angles. And we'll look at some of those harder situations on Monday. But right now, we have an ideal situation where a plane is flying due east at a velocity of 450 miles per hour, and then it crosses into a wind blowing out of the north at 20 miles per hour. So, whenever this happens, that wind is going to knock the plane off course a little bit. It's also going to change the velocity of the plane a little bit. So let's draw us a picture here. Plane is going east. The wind is blowing, be really careful with this right here, out of the north. So what direction is the wind blowing? South. So be really careful with that. You might see it on a quiz or a test. If it says out of the north, it's the opposite of, so it's going to be blowing to the south. So we've got this here. So the plane is flying east at 450 miles per hour. The wind is blowing to the south at 20 miles per hour, which I'm actually going to make this a little bit bigger just so we can see it a little better. But in reality, if we drew that to scale, it would be really tiny. So if we make a parallelogram here, and our resultant vector would look like this from the origin to the other edge of or the other corner of the parallelogram. This is what we're looking at. Let's label here, this is 450 miles per hour. This is 20 miles per hour, which means this also would be 450, and this would be 20. Alright, so the first thing it asks us is in what direction is the plane traveling. So you're looking for your angle when it says direction. I generally like to find the smallest angle. And I feel like it's more typically the answer that you see, although not always. You also could find this angle right here, but always make sure it's one of these central angles, one of these two angles right here where the origin is. You don't want to find these angles over here. You could, but it's more direct to find one of these two angles that actually touches north, south, east, or west. So if we look for this angle, here, Jaden, that 20, is that opposite, adjacent, hypotenuse? Is opposite. And then Jaden, what about 450? Opposite, adjacent, hypotenuse, adjacent. And you should see a trend here. We're always using tangent, right? So for these types of problems, we'll always use tangent. So tangent of theta is 20 over 450. So you'll do tangent inverse of 20 over 450. And whenever we do that, we get 2.545 degrees. And Jaden, what would I say for that? Is that north of east, south of east, east of south? What would I have for that? Okay. South of east. Good. South of east. And I think that's confusing. So sometimes I have to actually sort of trace my angle there. East is the direction that it actually touches. So that goes second. That's your main direction. And then you're going to the south of that. Possible they might also give 87.4 whatever degrees east of south. But I think it's probably more typical, especially with the really tiny angles, to see this. So the airplane's knocked off course by like 2.545 degrees. For part B, it asks us what the magnitude of the plane's resultant velocity is. So magnitude is speed, and that is represented by length whenever we draw these. So to find that, since this is a right triangle, we just have to do 20 squared plus 450 squared equals c squared. So 20 squared plus 450 squared is 202900. And we would square root both sides. And we get 450.444 miles per hour. Is our magnitude. Didn't make a huge difference on your speed there at all. But if you were, especially if this was early on in the trip and that wind persisted, it could make a pretty big difference in how far you're off. If you're off 2.5 degrees and you're going a long ways. So then, of course, it would be up to the pilot or the computers running the plane to correct that. There. All right. Okay. Here's another one that's a very physics-based sort of problem. So we've got a rope is pulling an object straight upward with a force of 50 newtons. Another rope is pulling an object towards the right with a force of 30 newtons. Find the magnitude and direction of the resultant force on the object. So if you imagine that we had some sort of object sitting here, maybe on a desk, and I give, if I give Lakin a rope and I give Justice a rope, and they're pulling in these opposite directions, then the object should kind of go upwards and to the right? So, you could imagine, like, if you're in, like, a situation where you've got maybe a crane here, you might have, the crane might lift the object straight up, but then you also might have to have workers that, you know, it can swing it around, but then at some point, you might have to have workers that have something attached to it to pull it into its final position. So you can kind of see how to do that correctly. So I always draw my little object right here at the origin. And I think these pictures are easiest to draw because it kind of makes sense. Here's your object, here's your rope that's connected to it, that's 50 newtons. And then here's the other rope attached to the object, and here is your rope that's pulling this way, and it's 30 newtons. And always ask yourself what makes sense. The other thing I'll notice a lot of times when students draw these, they don't put the endpoints and the arrows, and I would highly encourage you to do that, because if you think of what's happening here, if this if this rope is pulling up this way and this rope is pulling to the right this way, then the object has to go this way, right? So it's got to be sort of between those two arrows. If you don't have your arrows, you might draw this right here in, and it might seem like it makes sense because you don't know where the starting point on that case was. But always try to think about whether it makes sense that it's going, you know, in that direction. So we've got to make ourselves a parallelogram here. And our resultant vector from the starting point to the other corner of the parallelogram. So this would also be 30. This would also be 50. This one asks us for magnitude and direction of the resultant force. So magnitude, we're just going to do Pythagorean theorem. That's our length. So 30 squared plus 50 squared equals c squared. And so 30 squared plus 50 squared is 3,400. And we will square root that. And we should get that C is 58.30. Actually, it's going to be 310. Let me round that off. 310. And this is in newtons. It should make sense that that needs to be more than 50 or 30 because it's the longest side of the triangle, but it can't be any more than like 80 because 80 would be if you had two forces pulling in the same direction that you just add them together and you would get 80. But these are not the same direction, so they're going to not just add together. All right, questions? All right, and we also need to know the direction. Now, in these, direction is a little bit, you could give me a couple different things here. I usually just find the angle to the horizontal is what I usually look for. But it doesn't specifically state the angle to the horizontal, and it probably won't on these problems. So what I need is make sure you've got a picture drawn for me, and make sure your angle's shown on that picture. So if you choose to find this angle instead, that's fine as long as it's marked on your picture. Typically, I usually find this one right here. So if you find that one, you've got tangent of theta equals 50 over 30. So you'll do tangent inverse of 50 over 30. That is going to give you an angle of 59.036 degrees. What I don't want you to do on this, a lot of times whenever I give these problems, students will say it's 59.036 degrees north of east or something. If the problem doesn't have north, south, east, and west in it, you don't need to put north, south, and east and west in it in the answer. Because we're not talking about north, south, east, and west. We're talking about up and down and left and right. So it wouldn't be correct to put that north, south, east, and west in this problem. Okay, questions? Let's see. We're going to save this one for Monday. So, oh wait, we might need to do that one. Let me see if that, I may be thinking, okay, we need to do number 5. We're going to save number 6. We're going to do number 5 though. So, a wind is blowing at 45 miles per hour. The wind is blowing in a direction 30 degrees south of west. Find the westward and southward component. Let me tell you why you might want to do something like this. Let's say the wind is blowing at 45 miles per hour, 30 degrees south of west. So if we draw this in here, 30 degrees south of west, so the main direction is west. But it's going to the south of west here. So 30 degrees south of west, your 30-degree angle would be right here. And you know that that is 45 miles per hour. So let's say that your house is sitting right here, and its wall just faces this direction. It really doesn't matter how much force you have hitting that wall north or south. You really just care how strong the force is hitting this wall going to the west. So that is what's going to put the force on your house, right? That's what's going to knock it off its foundation, or, you know, bust your windows, or whatever happens there. So 45 miles per hour, let's hope you're okay, unless you've built your house out of straw or something. You should be okay. But if this was hurricane winds at 145 miles per hour, this could make a difference. Although those are usually not in a constant direction. But we want to know both the southward and westward component, but we're really interested in this westward component if this happens to be our house, right? So what we're going to do is we're going to draw in, basically make ourselves a parallelogram here. And so your vectors, you've got, this one is your westward vector that we have in red there. And then these two, these are your southward vector. You don't have to find direction on these. That's already built into the problem, right? What we've got to find is the magnitude of south and west. So if we're looking for our south, right here, I'm going to call that S, then that would be this one right here. I'm going to use this as my west. It really doesn't matter whether it's this one here or the one I drew down here, because they're the same length. I'm going to use this one up here because it's inside of that triangle that has that angle for me there. So I know in this case that Alright, so I know that this side is S, this side is W. I can't use tangent here, because if I use tangent, I've got south and west, and I don't know either one of those. So I know this side right here. I know 45. Alright, so let's say we're looking for south first. Okay? So south, if I know this is my 30-degree angle here, then Lyra, south, is that my opposite, adjacent, or hypotenuse? What is opposite? Good. And Lyra, what about the 45? I've got to use it because it's the only side I know. Is that opposite, adjacent, or hypotenuse? It's hypotenuse. So if I have opposite and hypotenuse, which trig function should I use? Sine. So I'm going to say sine of, in this case I know the angle, it's 30 degrees, equals opposite, which is that S that I don't know, and opposite and hypotenuse, which is 45. Okay, how do I solve that? Multiply by that 45, right, to get it. Since S is divided by 45, we'll multiply to get rid of it. So we're going to type in 45 sine 30, and we get 22.5. And that's miles per hour is our southward component. Make sure on a problem like this you label them south or west or whatever they are for me. Alright, now we need to go back and find westward. We could use this side that we just found if we want. I typically just like to use the 45 degree, the 45 side, because it's not rounded. So if I'm looking for W, for my westward component, then this is still my hypotenuse that I want to use here. Westward, that would be my adjacent. So if I have adjacent and hypotenuse, which one do I use? I'm going to use cosine. So I'll say cosine of 30 degrees equals adjacent, which is just the W that I don't know, over hypotenuse, which is 45. And I'm going to solve this one by multiplying both sides by 45. So 45 cosine 30 in our calculator, 45 cosine of 30 is going to give us 38.971. So 38.971 38.971 miles per hour westward. So, if my house is sitting here and this wall is facing towards the west, then I've got a force of 38.971 miles per hour pushing up against that wall. You can use law of sines. I would like for you guys to use regular trig for these, because there's a lot of things you're going to have to use regular trig for, and it's like, as long as they give you numbers, either one of them will work. If it's like ACT sort of problems or theoretical sort of problems, they give you letters, then setting it up with law of sines really won't work out that well for you. So, so on these, I would like for you to use regular trig for right now, just mostly to get some practice with that. But law of sines will also work for these. Okay. All right. So let me look at. You guys do have this very last slide, don't you? We're skipping several. I think you have this very last one. Let me look at the textbook and make sure all of these are ones I want you guys to do. 3, 4, 90. All right, so let's see, 13. Yes, 35. Okay, 40. We're not going to do 40 yet. Or 40 We're not going to do 40 or 41 yet. So what I want you to do is 13 and 35, and then the 1 through 5 that I have added here, because our textbook just does not have a lot of good problems on this, so I added some more in there. Do not do 40 and 41. We'll look at them when we do the problems that are a little bit. All right, so you got about 11 minutes here. Go ahead and start on that for me.